January 28th, 1986. Those were the years when NASA was challenging the skies and full of achievements. With the Mercury program, an American was sent into space for the first time in history. With the Gemini missions, both the first astronauts to survive hanging in the vacuum of space, and 2 spacecraft were able to dock in space. 8 of the 14 Apollo missions that followed reached the moon, making 6 landings carrying a total of 24 astronauts. 12 of these brave explorers wrote their names in golden letters in human history by walking on the moon, once considered inaccessible. After Skylab, the first American space station to orbit the Earth, the International Space Station took over the mission. The Viking program marked the first successful landing on Mars, while the Voyager program was the first to send spacecraft out of the solar system. Thus, the space race with the Soviet Union ended in ultimate victory, leaving behind a legacy that would inspire generations to come. However, what happened just 73 seconds after that launch would start a collapse from which NASA would not recover for years. This is the true story behind the series of mistakes that resulted in the deaths of 14 astronauts in front of hundreds of millions of people. And believe me, we have a lot to learn from this story, not only for space exploration, but also for our own lives. Although NASA's achievements were a tremendous source of publicity and inspiration for America at home and abroad, once it became clear that the Soviets were not going to catch America in space, NASA's budget began to erode rapidly. The budget peaked in 1966, on the cusp of man's first trip to the moon, but even then it only accounted for 4% of government spending. By the 1980s, it had fallen to 1%, and by 2023, it was down to 0.5%. So in the 1980s, NASA began to feel enormous pressure that it had to be self-funding to sustain its space programs. Otherwise, many programs would be shut down one by one. This pressure led to the germination of a revolutionary idea at NASA. The Space Shuttle program would be launched, transporting astronauts and experiments from institutions that wanted to conduct research in space and using the proceeds to finance other projects. While Elon Musk was meeting a computer for the first time in South Africa, NASA had already found a way to build humanity's bridge to space. To this end, NASA adopted an experimental method from the outset. Until then, rockets sent into space could not be reused, because none of their parts except the crew capsule would return. NASA developed the idea of a reusable rocket for the first time in history, and it could not only land the propulsion rockets back, as SpaceX has done today, but it could also land the shuttles it had launched into space as a whole, glide like an airplane, land on the runway, and then send them back into space again and again. Developed by NASA, these space shuttles had both strange and very cool designs. Known primarily as space planes, these vehicles, with their top-opening cargo hatches and robotic arms, were able to drop their cargo into space and also provided a living space for the crew. They were not really airplanes because they could not generate the power to take off from the ground with their own rockets. They could only land by gliding and landing softly on the runway. The shuttles were launched by rockets attached to the famous giant orange external tank. This orange unit, known as the external tank, was where the rocket fuel was stored. It had 2 compartments, one for liquid hydrogen and one for liquid oxygen. Shortly after launch, when the shuttle reached orbit, this tank separated from the body and burned up during re-entry. The only part of the system that was not reusable. There were 2 different rocket assemblies attached to the fuel tank. The first was a pair of solid fuel rocket boosters attached to either side of the external tank. These were the main boosters that lifted the shuttle for the first 2 minutes of liftoff. Once they had completed their mission, they would detach from the shuttle and parachute down to the ground, ready for reuse. The second group was the shuttle's own 3 main engines, which, fueled by an external tank, provided access to space and orbital maneuvers once the shuttle had ascended. At the time, these space shuttles, also called orbiters, because they did not have as extensive a staging point as today's International Space Station, could complete their missions by orbiting the Earth for periods ranging from a few hours to almost 18 days, as in the case of the STS-80 mission in 1996. Most of the missions were about putting satellites and observatories into space. The Hubble Space Telescope, the Chandra X-ray Observatory, the Magellan spacecraft, and the Ulysses Solar Probe, all of the telescopes and observatories you hear about, were sent into space by the Space Shuttle program. Most of the parts of the International Space Station were also carried by the shuttles, and astronauts sent for maintenance and research were also transported by the same method. The large payload volume allowed much larger cargoes to be carried into space at that time than today, either in one go or piece by piece. Not only satellites and telescopes were deployed, but also new equipment tests, trials of advanced flight techniques, crew replacements at the International Space Station, additional supplies and Earth observation missions were carried out by shuttles. At the beginning, the Space Shuttle program was running almost flawlessly. Shuttles were launched one after the other, and experiments from both military and civilian research organizations ran smoothly. However, despite all these improvements, the program was extremely costly. Analyses showed that at least 60 launches a year, that is one launch every 6 days, were needed to achieve a cost-profit balance. Yet by 1986, NASA had not achieved more than 9 launches a year. This put management under constant financial pressure, and the pressure fell on the shoulders of engineers. The rigorous inspection of parts returned from the shuttles, the replacement of worn parts and the repair of damaged parts, combined with the heavy workload, became extremely time-consuming. What's more, the engineers' maintenance, repairs, and upgrades were not easy, given the problems that arose in the shuttle's internal structure and rocket systems. It was in 1986 that Roger Boisjoli, an engineer at Morton Thiokol, a NASA subcontractor, realized a critical flaw in the design of reusable rockets. A rocket was not made up of a single piece, it was made up of many segments. These segments were connected by seals called O-rings. In NASA's designs, there were 2 rings connected one behind the other to prevent fuel from leaking out. Boisjoli and his team found that during cold weather launches, the first O-ring leaked fuel, but the second ring stopped the leak. This was an unacceptable risk for space shuttle missions. Boisjoli immediately reported the situation to his superiors. NASA officials took the warning seriously and quickly made improvements. Initially, the leak seemed to be under control, but on subsequent missions, the first ring became permeable again, and the second ring stopped the leak. Boisjoli reported that the problem persisted this time, but NASA changed the flight rules in light of its successes and pressing goals. It expanded the definition of minimal damage to include this level of leakage as an acceptable risk. Unfortunately, this approach foreshadowed the terrible Challenger disaster and the loss of our 7 astronauts in front of millions of eyes. Let's go back to January 28, 1986. Challenger was on the launch pad for its 10th flight and the Space Shuttle program for its 25th. NASA was now so confident that no one expected a disaster. On this flight, for the first time, a high school teacher, a civilian passenger, would be sent into space. Krista McAuliffe's flight, selected from thousands of teacher applications, would be watched live in thousands of schools. Apart from her, the crew was quite diverse. The shuttle's captain, Francis Scobie, was an experienced astronaut and pilot who had been in space with Challenger in 1984. Pilot Michael John Smith was a naval aviator who would make his first space flight. Physicist Ronald McNair would go into space for the second time, and space engineer and U.S. Air Force pilot Ellison Onizuka would make his second flight. Gregory Jarvis, who would conduct experiments for the private company Hughes Aircraft, would meet space for the first time with this flight. A team of fearless men boarded the Challenger's passenger cabin and buckled their seatbelts, unaware of an unexpected disaster. However, the night before the launch, temperatures plummeted to minus 7.5 degrees Celsius, and the ramp and all the equipment were frozen. On launch day, temperatures warmed to 2 to 2.5 degrees Celsius, 10 degrees Celsius lower than the coldest launch ever. NASA was now on the verge of an experimental zone. Previously, the launch had been postponed 6 times due to bad weather, technical errors, and scheduling conflicts. NASA was reluctant to postpone again, not with such high observation pressure and so many schools scheduled to broadcast live. The night before the launch, Morton Thiokol and NASA held an emergency teleconference in which engineer Roger Boisjoli strongly argued that launch should not take place until temperatures rise above 12.2 degrees Celsius. If this recommendation had been accepted, Challenger would have had to be delayed until at least April. NASA was under pressure to carry out a launch every week. On the other hand, engineers wanted to delay the next launch for months. At NASA's insistence, Morton Thiokol's engineers repeatedly reviewed their data, but found nothing to change their proposal. In response, Alan MacDonald, one of Thiokol's chief engineers and head of the Space Shuttle solid rocket motor project, made the right decision and announced that he would not sign the launch authorization. NASA, however, ignored this warning. Taking responsibility, it took the launch approval out of the hands of the engineers and left it in the hands of Thiokol executives. Company executives, whose sole purpose was to please their shareholders, could not be expected to listen to engineering decisions. Indeed, just 30 minutes after taking the authority away from the engineers, Thiokol executives signed the launch authorization. Thus, Challenger would be launched despite all the objections of the engineers. Apart from these minor details, everything up to the launch was routine. The countdown was called, and the rocket took off with a terrible roar. Can you see the problem? Take a good look right in front of your eyes. Let me show you. See those black fumes? Those fumes were extremely hot gases leaking from the rings on the bottom of the right rocket. And rest assured, those gases were not supposed to come out of there. So the destruction had already begun during takeoff, even though nobody realized it. The shuttle ascended smoothly for a minute after liftoff and successfully performed all the necessary maneuvers. There was a little more side wind than expected, but nothing the shuttle's control systems couldn't handle. As normal, the thrust engines were first reduced to 65% power, then increased again to 104%. Still no one noticed, but the leak was getting bigger and bigger, causing the left and right rockets to fire unevenly. Fortunately, the flight controller was able to compensate automatically, and the flight continued. But as the rings weakened under the intense vibrations and extreme fuel temperatures, more hydrogen began to leak out. About a minute after the launch, one of the cameras captured first a flash and then a fire where the smoke was seeping out. This fire grew in just half a second and began to destroy the structural integrity of the rocket. In the milliseconds before the final explosion, under unbalanced forces, first the oxygen tank began to leak. Then there was an explosion between the external tank and the shuttle, and the Challenger disintegrated and exploded in front of millions of spectators. NASA and the 7 lives entrusted to its care had fallen victim to a rush job. After the Challenger disaster, a 13-person Rogers Commission was established, including Neil Armstrong, the first man to walk on the moon, the great physicist Richard Feynman and Sally Ride, the first American woman in space, and all the events I have described so far were revealed in full detail. The most horrifying conclusion of the Commission's report was that the astronauts survived the initial explosion thanks to the shuttle's safety systems, but that they may have died from impacts or drowning because the shuttle crashed into the ocean just below the cabin at speeds exceeding 350 kilometers per hour and then took on water. However, we do not know exactly how they died, as telemetry and communications were completely cut off after the explosion. In the aftermath, NASA took a series of measures to ensure that such a mistake would never happen again. First of all, the solid fuel boosters were redesigned, and thanks to the new 3-ring design and the heaters added to those rings, the possibility of cold weather launches resulting in similar problems was completely eliminated. In addition, emergency protocols in the Space Shuttle program were changed and some equipment was replaced. An Office of Safety was established to oversee NASA. A project to take teachers into space was canceled, but in 1998 it was brought back as the Educator Astronaut Program. Barbara Morgan, a substitute for McAuliffe, the teacher who died in the Challenger disaster, was to become the first teacher to go into space on the Endeavour flight in 2007. It took NASA 2 years to resume Space Shuttle flights, but in this respect they should be congratulated. Instead of abruptly canceling such important missions because a mistake was made, they were able to take the necessary precautions and restart the flights. Indeed, between 1986 and 2003, NASA successfully took the space shuttles to space and back 87 more times. These flights made it possible to complete the International Space Station. You may be wondering why I've just taken the flights after Challenger back to 2003 and not to 2011, the year the program ended. Because on January 16, 2003, the 28th flight of Columbia, the first space shuttle built by NASA, would take place. And with the complacency of 15 years of successful flights, management mistakes would once again result in disaster. This time, it was the heat shields, one of the revolutionary innovations of the space shuttle at the time. These shields were not manufactured monolithically. They were made up of hundreds of small squares to cover the entire underside of the shuttle, including the underside of the wings. However, during the launch of the shuttle Columbia, a piece of paint foam covering the orange outer tank broke off and hit hard against the heat shields under the left wing. In fact, this should not have been a big problem, as similar breaks had been observed in previous launches. What was not realized at the time, however, was that the fragment was much larger than normal. Unfortunately, it was not immediately clear what kind of damage it had done to the shuttle. At least at that moment, it managed to get the 7-man crew into Earth orbit without any problems. For NASA, the terrible hours had just begun. Engineers on the ground routinely reviewed launch logs and discovered the collision on the second day of the mission. A committee of engineers, immediately formed by NASA and its subcontractors, United Space Alliance and Boeing, showed in their modeling that not only Columbia's heat shield but also the aluminum hull protecting it may have been damaged. This suggested that it might not be able to withstand the extremely high temperatures the shuttle would be exposed to during its return to Earth. To be sure, the committee wanted to photograph the wing from space using the Defense Department's observation satellites. But this would have required the shuttle to return to the satellite and interrupt the experiments it was currently conducting. Linda Ham, NASA's mission chief at the time, rejected this request and demanded that the experiments continue. According to Ham, the Department of Defense's camera resolution was not sensitive enough to detect such damage. Mission Control then ignored the damage and informed Captain Rick Husband and pilot William McCool on January 23, 2003, that there was an incident, but there is nothing to worry about. The crew also included veteran cargo commander Michael Anderson, the first Israeli astronaut Ilan Ramon, Indian-American Kalpana Chawla, one of the mission's 2 female astronauts, and U.S. Navy captains Laurel Clark and David Brown. It was under these terrible conditions that the crew entered the atmosphere at an altitude of 120 kilometers to land on Earth on February 1, 2003. Immediately, the extremely high temperatures began to rapidly melt the aluminum under the damaged heat shield. About 4.5 minutes after entering the atmosphere, the shuttle's sensors reported an overload on the left wing, but the controllers did not immediately notice the problem thanks to automatic stabilization. A short time later, a warning came that the left wing was overheating. About 9 minutes after entering the atmosphere, it crossed the coast of Columbia, California at Mach 23, or 28,400 kilometers per hour, 23 times the speed of sound. At this time, their altitude was about 71 kilometers above the ground. Just 30 seconds later, the Starfire optical telescope from Kirtland Air Force Base in New Mexico took these pictures of the shuttle. It was leaving a distinct debris trail behind the left wing, and observers along the Utah, Arizona, New Mexico, Texas line reported debris flying out from behind the shuttle. A minute and a half after that photo was taken, communication with Columbia was completely lost. Captain Rick Husband's last words were, "Roger that." At that moment, when the shuttle was still traveling faster than Mach 15, it began to rotate at 30 to 40 degrees per second, which meant that the crew was experiencing accelerations of up to about 3G. They were probably dizzy, but not yet in any fatal trouble. National records show that either Husband or McCool switched from autopilot to manual control about 30 seconds after communication was lost, so they were still alive at that point. But just 15 seconds after this move, the shuttle disintegrated and completely disintegrated. The crew had experienced a catastrophic death. The cause of death was not the forces of atmospheric entry, but the sudden depressurization caused by the rupture of the cabin. Normally, their helmets would have provided temporary protection, but forensic examinations revealed that some of them did not have their helmets on, and one astronaut's helmet was not on at all. This meant that the decompression happened so fast that there was no time to save them. In addition, the shoulder belts were not enough to keep the astronauts stable, and their heads hit their helmets and suffered severe damage. In addition, the astronauts probably suffered severe thermal trauma as high-temperature gases from the disintegrating shuttle filled the cabin. One crew member's clothing, for example, was completely ripped and torn off by exposure to the external winds of the shuttle's disintegration, and some were even showered with molten metal fragments. Eventually, the shuttle disintegrated on impact with land in eastern Texas. The only creatures that survived the catastrophic collision were C. elegans worms taken into space for experimental purposes. NASA launched a series of investigations from scratch. The damage was now too great to be easily overcome. The investigations showed that, if necessary, Columbia's mission could be extended by up to 30 days, so that the flight of the shuttle Atlantis, already scheduled for March, could be brought forward and converted into a rescue mission, possibly saving all the astronauts. Once again, excessive focus due to herd behavior and complacency from previous successes had brought death to NASA. After that, the processes were cleaned up and flights resumed in 2005, but the Space Shuttle program was terminated in 2011 after 22 more flights. At this point, NASA became dependent on Russian launch rockets for years. Then with the launch of private ventures such as SpaceX, it was possible to start sending astronauts from American soil again. As a result, the Space Shuttle program has carried 350 people from a wide range of backgrounds into space, successfully completing 133 of 135 flights on 5 shuttles in 30 years. In total, the astronauts spent 1,300 days in space, covering 872 million kilometers, and making extraordinary contributions to humanity with every move. Also, thanks to the Space Shuttle program, the Hubble Space Telescope was repaired 5 times, making it possible for it to continue its mission for so long. As a whole nation, we need to learn how to learn from mistakes in a lasting and realistic way. As you can see, overconfidence sooner or later leads to terrible mistakes, big and small, if companies and institutions are not kept under strict, independent scrutiny in good times as well as bad. The sharpest, most extreme frontiers of science, such as space, are so fraught with uncertainties that the slightest indiscipline is severely punished. Never forget that no achievement is too great to justify sitting comfortably in the seats that empower you to make decisions on behalf of the public. See you in the next video. Goodbye.